Let me start the presentation. First of all, I'd like to thank the organizers for giving me a chance to present the JSNS2 and JSNS2 experiment. I'm Jungsic from KK, Japan. First of all, I'd like to introduce the JSNS2 experiment. The full name is JPAC Sterile Neutrino Search at JPAC Spallation Neutron Source. More than 60 physicists are working together from 4 different countries. The experiment is located on the east side of Japan. Indication of a sterile neutrino was mainly driven by the LSND experiment from 20 years ago. The main goal of the JSNS2 experiment is a direct test of the LSND anomaly. To do this, the JSNS2 experiment is made similar to the LSND that uses the same neutrino source from the muon decay atlas, a similar flying distance of the neutrinos, liquid scintillator target, and detect neutrino signals through inverse beta decay. In addition, the JSNS2 experiment expects to reduce the accidental background significantly than the LSND, which will be explained later. We are willing to either discover the existence of the sterile neutrino or find the source of the anomaly. The JSNS2 experiment is running at JPAC and Materials and Life Science Experimental Facility, in short MLF. The left photo shows a part of the JPAC. MLF is located in the middle of the photo. A 3 GeV proton beam is mainly supplied to the MLF, and a small portion of the 3 GeV proton beam is injected into the main ring, which produces neutrinos for the T2K experiment. The JPAC provides a strong proton beam, which is designed up to the 1 MW beam power, periodically with 25 Hz. It is running with 0.74 MW now, but there was a 1 MW trial last June between 25 to 27, and it succeeded. Thus, we expect a continuous increment of the beam power. Moreover, the beam structure is a short pulsed beam, which is very different from the LSND case. There are 2 bunches in a single shot of the beam, as shown on the top right photo. The bunch width is around 100 nanoseconds and is apart from each other around 600 nanoseconds. The left figure shows a conceptual image inside of MLF. The mercury target is located in the middle of the MLF as indicated by a black arrow. A 3 GeV pulsed proton beam collides with the mercury target, produces many neutrons, pions, and kaons. The pions are decayed into muons, and extensive anti-muon neutrinos are produced by the muon decay atlas. The JSNS2 detector is put on the MLF third floor, 24 meters apart from the mercury target. The right figure shows the conceptual structure of the JSNS2 detector. It consists of a 17 tons target region filled with a gadolinium-loaded liquid scintillator as indicated by the blue color, a 35 tons gamma catcher, and a beta layer, which are optically separated and filled with the unloaded liquid scintillator. A total of 120 10-inch PMTs are observing the detector. The JSNS2 experiment took the first 10 days of physics data last June and has been taking the second long physics data since this January. The data taking is scheduled until the end of this June, with 6 months of data taking in total. Let me summarize the production and detection scheme of the experiment. A strong proton beam collides with a mercury target, produces intense muon neutrinos from muon decay atlas. Note that due to the shielding materials around the mercury target, most of pion minus and muon minus are captured before decaying. It increases the purity of the anti-muon neutrino source. those neutrinos could oscillate to electron antineutrinos during a 24-meter flight, then those will be detected in the JSNS scale detector through inverse beta decay. The prompt energy spectrum follows the well-known Michel spectrum, which is higher enough than external gamma background. The delayed energy spectrum is also well known from reactor experiments, which is higher enough than the environmental gammas. There are two notable things other than LSND. One is that JPAC provides a short pulse beam, thus we can search the signal in a very narrow timing region. It reduces the accidental background a lot. The other thing is JSNS scale uses the gadolinium-loaded liquid scintillator. It also helps a lot to reduce the accidental background due to the higher gamma energy and short capture time. Operation-wise, JSNS scale should overcome very special thing. The JSNS scale detector is put in the maintenance area for the mercury target and beam equipment. Thus, the detector should be going out to the MLF during the summer maintenance period, and the detector cannot be transported with the scintillator field due to the fire law in Japan. Thus, we should empty the detector every summer and fill the scintillator again before taking data around the end of each year. It was very challenging work, however, we have overcome it through very careful preparation. So last June, we filled and emptied the detector once within several working days each. It's very fast for the physics run, and the last December, we had filled the scintillator again within 3 working days. And we did not observe any considerable degradation of the scintillator quality. Let me show you some photos. The top left photo shows the detector with a special low-band trailer. The top middle photo shows the detector and 3 so-called ISO tanks, which are filled with the scintillator. The top right data shows the scintillator level during the first filling, physics data, taking, and extraction. The bottom left photo shows the detector positioning with a 130 tons grain. You can see the part of red blocks for the passive shielding. Finally, the bottom right data shows the scintillator level during the second scintillator filling in last December. Last year, the beam power was 600 kilowatt. However, it was increased up to 740 kilowatt since this April. The increased beam power was very stable since then, and it reaches 2 months already. During the first physics run, we took 8 times 10 to the 20 POT, which was 0.8% of the approved POT by the JPAC PAC. The main purpose of the first physics run was to confirm the detector working and valuable feedback to the next long physics run. This year, we have already taken more than 10 to the 22 POT, which is 10% of the approved POT. The right graph shows the acquired POT from this January. Note that there are 2 relatively long flat regions. One was the N2 purging campaign early of the data taking, and the other was a long-term scheduled BMOB in May. The DAQ efficiency is more than 95%, which means very stable. And from the feedback of the first physics run, we have implemented a very efficient stellar neutrino trigger additionally, and many interesting analyses are ongoing, and I will introduce some of them from now. For the beginning, we have taken several californium source data. The left histogram shows the charge distribution of event with and without the californium source before applying any coincidence. One can see the clear excess due to neutrons captured by gadolinium. The middle graph shows the californium source position versus the reconstructed G position, and the right histogram shows the reconstructed energy of neutrons captured by gadolinium. The measured energy and vertex resolution was similar to the predicted values from the Monte Carlo simulation. Thus, we conclude that the detector was working well. The next thing was to investigate the number of each background and compared them with the expectation in the technical design report, which is available on the archive. We have been focusing on them, especially the background shown in the red dashed box. As you can see, the dominant background comes from the accidental, even after assume a strong delta vertex cut. Thus, it is essential to check the singlet of the accidental background source. It dominates from cosmic gamma, which will be explained next page. In JPAC, there is a maintenance day per week, and a beam is not provided during the maintenance. With data that has been taken during the maintenance, we can separate the beam uncorrelated backgrounds and the others. The black dot on the left plot shows the self-legal data. Many different contributions are there, thus we have categorized contributions from each particle with the coincidence technique except the muon. Muon events were separated from the beta PMT's information from the beginning. Finally, the residual events were assigned as cosmic gammas, which are the main source of the accidental background. One can see the estimated trigger rate from each particle, such as Michel, fast neutron, cosmic gamma, and muon on right side with numbers. The single rate of cosmic gamma in the stellar prompt energy region was around 58 Hz, and in the stellar delayed energy region was around 100 Hz. Note that we put somewhat conservative, around 20% systematic uncertainties to all values now. As I explained the earlier part of the presentation, JPAC provides a very short pulsed beam, thus the time window to select IBD is very powerful to reject them. Per spill, the reduction for IBD prompt is 10 to the minus 5, and for IBD delay is 10 to the minus 4. For the next step, let's move on to background activities around the beam timing. Accidental is the main background, and if we convert the cosmic gamma ray of the previous page, after considering the IBD prompt and delay time window, it gives the accidental background rate per spill, which is written in red color on right side. As you can see, the numbers are consistent with the expected values within a factor of 2. Note that we did not apply any fiducial code to select target events only, thus the red-colored numbers will be reduced more. The other notable thing is, due to the MLF facility structure, some additional gammas, we call them to hatch gammas, can go into the JSNS scale detector if and only if there is a beam. We are estimating the accidental background due to this also. To reject the fast neutron background, which is the main correlated background, we will apply the well-known PSD method. For the demonstration purpose, we gather gamma-like and neutron-like samples from the data, as shown in the left figure. One can see the clear difference from averages PMT waveform. We are developing two different methods. One uses likelihood and the other uses machine learning to maximize the PSD power. From here, I'll change gear and introduce the JSNS2 experiment, which is a reasonable expansion of the JSNS experiment with a second detector. More detailed things are well described in the proposal, which is available on the archive. In short, we have proposed to put a second detector near but outside of the MLF is shown in the left photo to the JPAC PAC this January. And stage 1 out of 2 stages was approved. The baseline from beam is around 48 meters, twice longer than the JSNS2 experiment. We are considering building the second detector with a similar concept to the current JSNS2 detector, but twice larger volume. Recently, Diabase donated 40,000 liters of GDLS and 60,000 liters of LS. They have already been installing in Japan and ready to use. We'd like to appreciate it to Diabase. One of the biggest merits of the two detector configurations comes from the difference in oscillation probabilities as shown on top two plot. The bottom two histogram shows the expected number of events if we assume the LSND best fit value. The left histogram assumes a total of 8 years running with the JSNS2 detector only, and the right histogram assumes a total of 5 years running with the second detector only. We expect some cancelling of the systematic uncertainties also. We estimated the sensitivity of the JSNS2 experiment. Compared with the current JSNS2, the sensitivity becomes better, especially lower delta M-square region due to the long baseline. With 5 years of running of two detectors after 3 years running of the current JSNS2 detector, we expect to cover most of the LSND indicated region with a 3 sigma confidence level. Note that huge flux uncertainty was assumed here, thus the sensitivity would be better if we could reduce the flux uncertainty from other experiments. We are doing our best to realize the JSNS2 as soon as possible as shown on the timetable. We submitted the proposal last year and got stage 1 approval of 2 stages this year. We aim to submit the technical design report of this year. We are discussing with companies to build the detector vessel. PMTs are assumed to be delivered next year. GDLS and LS have been installing in Japan already. Electronics are under consideration. The ultimate goal is to start data taking from the end of 2023. Let me summarize. JSNS2 aims to test the LSND anomaly directly with identical method, but with a smaller accidental background. We took the first physics run last June, and the second physics run is running since this January. Many interesting analysis is ongoing. JSNS2 using a new detector is newly proposed. It will improve the sensitivity, including the lower delta M-square region, and the grant was approved. It will be a similar concept to the current JSNS2 detector, and Diabase donate the GDLS and LS. Thanks a lot. And many works are ongoing in parallel and aim to start data taking from the later in 2023. Thanks for listening to the presentation.